Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on nonlinear control systems. Today we are going to discuss controllability and observability for nonlinear systems, and let's get started. So the controllability of nonlinear systems is going to be tied to the concept of Lie brackets. So before we discuss the controllability of nonlinear systems, we shall be going through this concept of Lie brackets, and we shall see what Lie bracket is and how do we define a Lie bracket. So Lie bracket can be thought of as a derivative of a vector field with respect to another vector field. So the exact definition of Lie bracket would come later on in this lecture, but this is the concept of Lie bracket, that it is a vector field, the derivative of a vector field with respect to another vector field. So nonlinear observability is tied to the concept of Lie derivatives. Lie derivative is basically derivative of a scalar function along a vector field. So we shall see what Lie derivative is and how we define Lie derivative before we discuss the concept of observability for nonlinear systems. In this lecture, so the whole discussion of controllability and observability will be more than one sessions. So in this session we shall be discussing only the controllability part, and in the next session we shall be discussing the observability for nonlinear systems. So first of all, let's look at a differentiable vector function on Euclidean space. So consider a differentiable vector function f, which is a function from Rn to Rn, which means that f operates on a vector n-dimensional vector, and the result of applying f to an n-dimensional vector is also an n-dimensional vector. So such a function forms a vector field over a set of points x belong to Rn. I am not in this section. I am not going to go over the definition of a vector field. You can look at it in the lecture notes that I have provided you regarding the first couple of lectures of nonlinear control systems, and you can also refer to the definition of vector field using online search. It's a pretty simple concept. Basically it says that whenever you add these type of functions, the result of the addition of functions should also be the same type of function. So vector addition and scalar multiplication does not alter the class of functions. So if a function from Rn to Rn, if you add it to another function from Rn to Rn, if the result of the addition is yet another function from Rn to Rn, then this is one of the requirements of a function being a vector belonging to a vector field or forming a vector field. So what is Lie bracket? Once you understand that this function f forms a vector field over the n-dimensional Euclidean space, then consider two vector fields fx and gx on Rn. Then Lie bracket operation generates a new vector field which is defined by f comma g. So this is like a bracket notation, and it is defined by partial derivative of g with respect to x multiplied by f of x minus partial derivative of x with respect partial derivative of f with respect to x multiplied by g of x. So this definition is not very complicated. So you can see that you have two functions of x which are vector functions, and you take the derivative. You already know that or I hope that you know that the derivative of a vector with respect to another vector is a Jacobian matrix. So you calculate the Jacobian matrix of g with respect to x and multiply this Jacobian matrix with a vector f of x. So matrix multiplied by vector will be a vector. minus this will be another Jacobian of f with respect to x multiplied by g of x. This will be a vector. If you subtract one vector from another vector, this will still be a vector, and this vector will be a function of x which will belong to this class of functions. So it will still be a vector field, it will still be a vector field. So it will be a function belonging to the same vector field. This is the definition of Lie bracket. I just want you to hold on to this definition for the time being, and then we discuss this a little bit further. So we can also define higher order Lie brackets. For example, before I go into higher order Lie brackets, I just want to let you know that this bracket of f comma g can also be written as adjoint of first adjoint of f with respect to g. So it is like AD stands for adjoint. So if you look at higher order Lie brackets, then the zeroth adjoint of f with respect to g is g itself. First adjoint of f with respect to g is Lie bracket f comma g, which we have defined in the previous slide, and then the second adjoint would be adjoint of f with respect to the first adjoint of f with respect to g. So this will be f comma Lie bracket of f comma g. So if you take the Lie bracket of this thing, then that will be second order Lie bracket, and then you can continue on in this manner, and that will give you, like, you can proceed up to whatever order you want, k, and that will be the Lie bracket of f with the Lie bracket of k minus 1 adjoint of f with respect to g. So in this way one can define the higher order Lie brackets, and we will also look at some examples by the end of this lecture. So now that we have discussed what Lie bracket is and how we define Lie bracket, we can start our discussion on controllability. But before I discuss the controllability for nonlinear systems, I just want to recap the controllability for linear systems. So we already know that for linear system of the form x dot equal ax plus bu, where x belongs to Rn and a belongs to Rn cross n, u is m cross 1 vector in general for multiple input system, and b would be r of n cross m. So for this type of system, we have a controllability matrix b, ab, a square b, and up to so on an minus 1b. So this is the so this is n. This is the first m columns of Q matrix. Then this is the next m columns. This is the next m columns. So number of columns in the Q matrix in general is n multiplied by m. But for controllability, all we need is the Q to have full rank. So number of rows in Q is n, and n is smaller than n multiplied by m. So highest possible rank of Q matrix would be the minimum of the number of rows and the number of columns. So in this case, number of rows is less than number of columns, so the highest possible rank of Q could be equal to number of rows, which is n. So if Q has rank n, this n, so if Q has rank n, then we would say that this system is controllable, and if Q is Q has rank less than n, then we would say this system is not controllable. So this is controllability for linear time invariant. Okay, so next I want to just rearrange a few things by I want to define a little bit of a new notation for this linear systems, so that when we transition to the nonlinear systems, it might help in understanding the concept of controllability for nonlinear systems. So we can actually make this system x dot equal ax plus bu. We can think of b in terms of different components and also u in terms of different components. So we can write b into u as b1 u1 plus b2 u2 plus up to so on bm um. So if you multiply out if these terms, this basically is this is same as, so b1 is the first column of b, b2 is the second column of b, and so on, bm is the mth column of b. So you already know when a matrix multiply with a vector, then each the result of matrix multiplication with a vector is always going to be the linear combination of the columns of the matrix with respect to components of the vector. So this is a simple linear algebra that I have used here to show b as sum of components or columns of b which are multiplied with different components of this input vector u. So next I define f of x to be equal to a times x. So this term I defined it as f of x, and similarly I define b1 to be equal to g1 of x, and b2 to be equal to g2 of x, and so on, bm equal to gm of x. So g sub I of x is equal to b sub I. So this is just a notation, a way of a different way of writing the same thing. So in this case, if I define f of x and g of x like this, then f Lie bracket of f with gi would be partial gi by partial x into f of x minus partial f by partial x into gi, which will be, in this case, since g does not depend upon x, it is constant. So the derivative of a constant with respect to vector x would be 0. And then derivative of f with respect to x, this is easy because of the way we have defined f of x. So f of x is a times x. If we take the derivative with respect to x, then it will be simple a. And if you multiply a with g sub I of x, this will be b sub I. So minus sign will carry along, and so the Lie bracket between f and gi would be minus a times b sub I. So this is something that I want you to remember for some time. So next let's try to look at some higher derivatives of this system. So if we take the second derivative of x dot equal ax plus b1 u1 plus b2 u2 up to so on, then since there is no x in these terms, when we take derivative with respect to x, these terms can become 0, and this term will have become a times x dot. So x double dot will be a times x dot. We are assuming that u is constant with respect to x. So next, if we keep on going, then this x dot can be replaced with this whole expression of x dot. If we substitute the relation of x dot into this expression of x double dot, then we get a square x plus sum of I equal 1 to m a multiplied by b sub I u sub I. So this is the expression for x double dot when we substitute the value of x dot into that one. So this, you can see that a multiplied by b sub I is basically the negative of the Lie bracket between f and g. So we can write it as, the negative sign will come out of summation because it appears in all the Lie brackets. So we'll say that Lie brackets between, it is the sum of Lie brackets of f comma gi multiply by ui. So we are not doing anything with ui, so it comes here as it is. So x double dot is a square x minus sum of Lie brackets. So you can see that this is the whole same system, and I'm just by defining this type of notations, I am getting the higher derivatives of x in terms of Lie brackets. Alright, so I keep on going. I calculate the third derivative of x. This will result in a cube times x plus sum of a square bi ui, and if you take the second order Lie bracket, that will turn out to be plus a square bi, and so you can write a square bi as the second order Lie bracket of f with respect to gi. And here you can notice that the sign has become positive, because if you take, so this is already negative. If you take the Lie derivative of this minus a multiplied by bi with f, which is a times x, then again this is independent of x, so the derivative of will be, this term will become 0, and this term has a minus sign here, and there will be a minus sign in, instead of gi we will be having this minus a bi term, and then this minus minus will become plus, and partial f by partial x will be a, so this will become plus a square bi. So second order Lie bracket will be plus a square bi. First order was minus sign, second order would be plus sign. And similarly, if you want to take third order Lie bracket, then again it will be minus sign. Fourth order will again be plus sign, and fifth order Lie bracket will again be minus sign. So sign will toggle, and the powers of a will pile up. And then we continue on in this fashion. This I have repeated from previous slide, and if we continue on till the nth derivative of x, so nth derivative of x will lead us to a to the power n times x and minus 1 raised to the power n minus 1, because the minus sign will be toggling with each power, so that is catered for with this term, and then there will be Lie bracket of the order n minus 1 inside the summation. So what is the purpose of writing all of this stuff? The only purpose is to show you that the span of the higher order derivatives of x is with respect to, has something to do with the Lie brackets. So if we write the controllability condition for x dot equal ax plus bu in terms of fx and gx and Lie brackets, then it will turn out to be something like this. So Q matrix will be G1, G2 up to so on Gm. So G1 will be the first column of Q matrix, this is the second column, and this is the mth column, and then again this will be the next column, and so on. So this will keep on going, and if you compare this with the original Q matrix, then actually this is the same as the original Q matrix, because remember G1 is B1, which is the first column of B matrix, and G2 is B2, which is the second column of B matrix. So G1 through Gm, this is basically same as B. So Q matrix has B, Q matrix starts with B, then there is A into B, which is the first Lie bracket. So remember, first Lie bracket is A into B. The plus or minus sign does not change the rank of the Q matrix. This you can know from the matrix theory. And then the higher order terms like n minus 1 Lie bracket of f with respect to G1 up to so on Gm would correspond to a to the power n minus 1 into b. So this is the same controllability matrix in terms of Lie brackets. So one could ask this question, that why going through this whole exercise and why showing you that the controllability matrix is actually, it also can be written in terms of Lie brackets. The whole purpose is that the controllability that we are going to discuss about nonlinear systems is going to be in terms of Lie brackets. So this is just to give you an idea that linear systems is basically nothing but special case of a nonlinear system. So the controllability condition for linear systems is a special case of controllability condition for a non-linear system. So that was the purpose. And why going to the nth derivative of x. So if you remember the Cayley-Hamilton theorem, it states that the span covered by the powers of a matrix A, the system matrix, does not increase if you increase the powers of A beyond this n, which is the size of the state space. So similarly, the span of all the derivatives of x cannot go beyond n minus 1 order Lie bracket. So this was just to confirm that we have to, so we start with G, we keep on taking the Lie brackets. So up to which bracket do we like, which is the bracket order where we stop? So this is the bracket order where we stop, because if we take another higher order derivative of x, that would yield a to the power n plus 1, and the span of that derivative would be overlapping with the existing span that we achieve with the first n powers of A matrix. This is a little bit complicated, but you just have to deal with it and try to think about it until you make your peace with this concept. Okay, so next we start looking at the nonlinear systems, and we shall be looking at nonlinear affine systems, as you may already have guessed, because that's how we wrote down the linear system. So we wrote down the linear system in this form, where f of x was a times x, and gi times ui was bi times ui. So that was the linear case of the affine nonlinear system, and now we are going to discuss the full actual nonlinear affine system. So there is a theorem about local accessibility for a nonlinear system. So the above system, which is a nonlinear affine system, is locally accessible about a point x naught in Rn if the accessibility distribution Q spans Rn. So if where Q is defined as this matrix. So you can look at Q that this is same as the linear case, but the difference would be that here G1, G2, G3 would not necessarily be constant column vectors. Those would be in general nonlinear functions of x. So nonlinear vector functions of x. So there will be G1, G2, up to Gm, and then there is Lie bracket between all possible pairs of G. Lie bracket of G1 with G2, G1 with G3, G1 with G4, and so on. And then there are Lie brackets of higher order Lie brackets of G with respect to other G's. And then there are Lie brackets of f with respect to G, and higher order Lie brackets of f with respect to all the G's, and it keeps on going, but you don't have to have this matrix infinitely long, infinite number of columns. You will see once we do some examples, you will see that how much of these brackets are enough. So in general we are only looking for n independent columns. So if we find n linearly independent columns, that's good enough for us. And if you compare this with the linear systems case, then you will see that Gi terms are analogous or similar to the B matrix or columns of B matrix terms, and then these terms are new. So there is no corresponding term in the linear systems Q matrix. So you can say that these are the terms for specific to the nonlinear systems, and then these terms correspond to the AB terms in the linear systems case. So this is the theorem, This is the controllability. Well, this is not controllability, this is local accessibility. So accessibility at a point x naught, so you have to calculate accessibility at every point. So if a system is accessible at every single point in Rn, then you can say that it is controllable. So there is another a condition for controllability, that if f of x is 0, if this term is 0 in the nonlinear system, and then x dot equals sum of all gi times ui, then in this case if this matrix has rank n, then the system is controllable, which means that it is accessible at every single point. Of course, when f of x is 0, then all of these brackets will be correspondingly adjusted, or you may not even need them. Okay, so let's look at some examples. So consider this third order system, 3-state system. Then you have x1 dot equals sine of psi into u1, x2 dot equal cos of psi u1, and psi dot equals u2. So this is you can think of it as a robotic arm, the joint of a robotic arm, and there are like two inputs. One input is going to rotate the xy coordinates of the arm, and this could be the torque related equation. So this system is basically of the form x dot equal f of x plus g1 times u1 plus g2 times u2. How is this system of this form? Let's see. So consider x to be a vector of x1, x2 and psi. So you can see that this is x dot, this whole thing is x dot, and then f of x would be 0 0 0. So we have x dot equals 0 plus some g1. So g1 would be sine of psi, cos of psi and 0, which will mean that g1 x1 dot is g1 times u1 plus g2 times u2, where g2 is 0 in the x1 dot case, and g2 is 0 in the x2 dot case as well. But in x3 dot, g2 would be 1, whereas g1 would be 0. So you can relate this form with the given example. So given this system where we have x like this, f of x equals 0, g1 and g2, how do we form the Q matrix? It's very easy. You just have g1 and g2, and then the bracket between g1 and g2. You don't need any other higher order brackets because you only need Q to be of rank 3. So if these three are enough to prove that Q has rank 3, then we don't need any other brackets, that like we don't need higher order brackets of g1 and g2. But if these three are not enough, then we can try to look into higher order brackets and see if there is any possibility. So in general you will know this without much effort So let's see what Q turns out to be. So we already know G1 and G2. So this is the first this is the first column of Q, this is the second column of Q, and we are looking for the third column of Q, which is the Lie bracket between G1 and G2. If you the definition of Lie bracket would be partial G2 by partial X into G1 minus partial G1 by partial X into G2. And you can see that G2 has no X in it, so it's a constant with respect to X. So this term partial G2 with respect to X would be 0. So we only have partial G1 with respect to X, which will be the Jacobian of G1 with respect to X. You can see that G1 only has the third component of X, so it does not have x1 and x2. So first two columns of the Jacobian would be 0. and the third column of Jacobian would be the derivative of g1 with respect to the third component of x. So sin psi derivative would be cos of psi, and cos of psi derivative would be minus sin of psi, and 0 would have 0 derivative. So multiplying with this with g2, if you multiply that, you have minus cos of psi, sin of psi, and 0, and the final Q matrix will become like this. And you can see that whatever the value of psi you plug in, this matrix will always have rank 3. So Q matrix has rank 3 for all x, which means that at every point x0 it is accessible, and so this system is controllable. So we already saw that f of x in this case is 0, so its accessibility would imply the controllability. Alright, so this was the first example where the nonlinear system turned out to be controllable. Let's look at another example. So consider the second order system where x1 dot equal x2 square and x2 dot equals u, and then in this case f of x would be x square x2 square and 0, and g would be 0 and 1. So there's only one g and one single, this is a single input system, so we can see that the Q matrix would become g and f bracket g. We don't need to use the higher order brackets of f comma g unless we need to, unless these two brackets fail to get Q a rank of 2. If these fail, or in general you will see that the higher order brackets will turn out to be 0 as well. So the Q will never be Q will almost never have infinite number of columns, only as many columns as the size of the state space would suffice to determine the controllability or accessibility. So we can see, we already know the g here, it is 0 1, this is the first column of Q. We only need to calculate f comma g, which you can easily calculate using the definition of Lie bracket, and it will turn out to be minus 2x2 and 0. And if you plug it right here, this matrix would be rank 2 if x2 is non-zero. If x2 is 0, this whole column will become 0 and the rank of Q will drop to 1. And even if you use higher brackets of f comma g, this condition will not change. So Q will always lose its rank at x2 equals 0. And so this means that Q has rank 2 everywhere except for the points with x2 equal to 0, and x2 is 0 along x1 axis. So along the whole x1 axis your system is not accessible. Therefore the system is accessible everywhere except for the points on x1 axis. So this was another example where the system is not controllable, but it is accessible at points other than the x1 axis. So I hope that this examples and the description of the nonlinear controllability was useful in understanding the concept of controllability for nonlinear systems. In the end, I just want to give one remark, that if we linearize a nonlinear system about some point x0 and the linearization is controllable, then the original nonlinear system is accessible at x0. And we already saw that in earlier lectures that if the linearization of a nonlinear system around an equilibrium point is controllable, then it is possible to design a feedback control law for the original nonlinear control system, which means that when the only way you can have a feedback control law that would be stabilizing feedback control law is when the system is controllable or at least stabilizable. So but this is not true the other way around. That is, if the linearization is uncontrollable, then it does not mean that the original nonlinear system would be locally inaccessible, original nonlinear system could still be accessible. So in this case, if the linearization is uncontrollable, then you have to check the nonlinear controllability by using the definition that we have discussed in this lecture. But if the linearization turns out to be controllable, then the accessibility of nonlinear system is implied. So this was the remark I wanted to make before ending this lecture, and in the end, like I always try to do, I would revise the whole lecture in a couple of minutes, and we'll see what we have discussed today. So here we started with the notion that nonlinear controllability is related to the Lie brackets, and the Lie brackets can be thought of as a derivative of a vector field with respect to another vector field. And you can see that g of x is a vector field, and g of x with respect to x in Rn, which is basically x of n is in itself is a vector. So nonlinear observability, we shall discuss that next time. And then we consider the vector field f of x in n-dimensional space, and this is the Lie bracket, which is sort of similar to a derivative of a vector field with respect to another vector field. So derivative of a vector with respect to a vector is a Jacobian. So higher order Lie bracket, that would be similar to the Lie bracket. You take a Lie bracket and take the bracket of a bracket. So you take the bracket of f with respect to the bracket, then this will be the second order bracket. So if we take a bracket with respect to a k minus 1 order bracket, then that will be kth order bracket. Similarly, we looked at controllability for linear systems, the B, AB, A square B matrix. This was simple. Then we redefined the notation in order to show you that for linear systems as well, the Lie brackets are involved in controllability. We define f of x equal ax, g as column of b, and then Lie bracket was a times b. Higher order Lie brackets would be higher order powers of a times b, and then the minus sign would toggle. And then we looked at the controllability matrix of linear system in terms of Lie brackets, where you can see that G1, Gm correspond to B, first order bracket corresponds to A times B, and n minus 1 order bracket correspond to A to the power n minus 1 times B. And then we discussed the nonlinear systems local accessibility condition, and then we looked at the condition special case where controllability is implied. And then we looked at a couple of examples, a third order example where we had G1 and G2, and then we calculated the Q matrix. We just considered the first three terms, and it turned out to be full rank, so we don't have to consider the higher order brackets. Same here, don't have to consider the higher order brackets, and it turned out to be locally accessible at everywhere except for the points where x2 is 0. And then finally a remark that the linearization, if linearization is controllable, then the nonlinear system is